Welcome, dear civil engineering students and faculty members. Yeah, this is all about moment distribution method, where a sway frame is taken as shown in the figure, and the sway frame has a span of 0.5 meters, and the height of the frame is 0.25 meters. And we are applying a load of 4.9 Newton at a distance of 0.2 meter from the point B and 0.3 meter from the point C. So here we go. In Galgotias University, we have next gen structural analysis laboratory, and we will perform the moment distribution method and cross verify with the calculations from the machine. So regarding this portal frame is actually the frame which is subjected to sway because the loading is unsymmetric, and we take the flexural rigidity EI as constant for all the members AB, BC and CD. Proceeding further, you can see that this problem is split into two types, where you are arresting the sway at this location and perform non-sway analysis, and in the second part you are going to perform the sway analysis by allowing a deflection delta. So delta is the deflection allowed. Now you can see that the same problem is divided into two parts, and these two parts will be analyzed separately by moment distribution method. Here we go. In the first non-sway analysis, we find out the stiffness coefficients KBA, KBC, KCB and KCD, and these are the values finally that we have arrived. And proceeding further, we will also find out the fixed end moments. Since there are no lateral loads or any UDL loads in the members AB and CD, we don't care about the fixed end moments. We only calculate the fixed end moments for the member BC and CB. So you can see that minus WA times B square by L square is equal to minus 0.352 Newton meter, and similarly for fixed moment CB we have WBA square by L square, and that yields 0.235 Newton meter. Then as you see here, we have already calculated these stiffness coefficients, and from these stiffness coefficients we calculate the distribution factors, and you can see the values of distribution factors calculated here in this table, and their values are represented here. Now this is the non-sway analysis. In non-sway analysis, we write down the distribution factor for BA and BC, CB and CD and DC. Here you write for AB. Then you write down the fixed end moments calculated. Once you have write down the fixed end moments calculated, you neutralize the moment at these joints B and C. For example, minus 0.352 is balanced by plus 0.352 times 0.33, that is written as 0.11616, and 0.67 into plus 0.352, that is written as 0.23584. Similarly, you balance the moment 0.235 by providing moment in opposite direction and multiplying the same with distribution factor. Once you do that, you carry over the moments as shown in the figure. So half of the moment is transferred to the farther end. So for example, from this point, the farther end is half of the moment is transferred, and for the point C to D, half of the moment is transferred. Once you compute the carryover factors, carryover moment, you are left out with some moments in the joints B and C. Similarly, you in the opposite direction, you apply moment with the distribution factors being 0.33 and 0.67. So this row is for balancing. Similarly, the same procedure is repeated until and unless you get consequently the same values or the values nearing zero. Then once the value is nearing zero, you stop at balancing and estimate all the fixed end moments, all the final moments that is being estimated here. Once you are done with the final moments, you can calculate RAH is equal to MA plus MB by H, which is said to be 1.614 Newton, and RDH equal to minus 1.21 Newton. And what is the sway force? Sway force which is going to create the deformation or delta S, R is equal to 0.403 Newton. This is the force needed to prevent the sway. And actually here the horizontal equilibrium is not satisfied. That means you can see that summation of h equal to 0 is not satisfied by having a sway force of 0.40361 Newton. So to do that, what we have to do is we have to allow the deflection to happen. For example, what you can do is you take the frame, and for this frame you apply a sway force of 0.403. So what happens is it bends like this, where you have delta at these locations. So we will try to estimate what is the deflection by using the sway analysis. So for that, what do? We assume that the sway happens at this towards right. So once you assume this, you can calculate this R star. So this force is the sway force, which is corresponding to the sway delta. But in the previous case, we don't know what is the sway created. That's why first we will find out this R star sway force, which is for an arbitrary deflection delta. So apply a deflection delta, then using that you estimate the fixed end moments. Once you are done with the fixed end moments, you assume that the delta is equal to 1 by 96 EI. Substituting here, if you divide this minus 96 EI by 1 by 96 EI, you are getting the values as -1, -1, 0, 0, -1. Now, how to do the sway analysis? You substitute the fixed end moments at these locations. For example, -1, -1, and -1 and -1. Once you are done with that, then you go for balancing. For example, at joint B, you have -1. -1, to balance this, you apply a moment in opposite direction, which is said to be 1 units. Now 1 multiplied by 0.67 you get here, 1 multiplied by 0.33 you get here. Similarly, for the joint C and joint B, you have to apply opposite moments and distribute that using the distribution factor and balance that. For example, if you add these two, 0.67 plus 0.33 is +1, and +1 minus 1 is 0. But however, once you apply these balancing moments, half of the moment is transferred as carryover factor to the further end. So from this we can see these arrow marks represent the transfer of the half of the moment to the further end. Now you are end up with these moments, this moment at B, and similarly this moment at C. Similarly, you do the balancing and you repeat the process. Once you are getting values nearer to 0, you stop the balancing and estimate the final moments which are given in the row. So this row consists of the final moments which is due to the sway delta. Let's see how we proceed further. Then what do? We already know this 0.7125 and minus 0.425 minus 0.425 minus 0.7125. Using this, you estimate what is the value of RH and RDH. So that is nothing but the summation of moments divided by H. That is summation of MA plus the MAB plus MBA divided by the H equal to RAH. Similarly, for this case, you take for DH. So for this one, you take the moment at this location, that is MCD plus MDC divided by the height of the frame. Then you will get RDH. Once you are done with this, this is the final sway force, which is equal to addition of these two forces. Now you can see that that will be in opposite direction. So you are getting plus 9.1 Newton. Now, what is K? K is the coefficient, which is the coefficient which is defined as the ratio of the real sway force divided by the arbitrary sway force. So that you are getting 0.0444. Once you are done with this, you write down the arbitrary moment. So these are the arbitrary moments M star. Then you multiply it with K. This whole row is multiplied with K and it is represented as K into M star. These are the non-sway moments. So you are going to add these two and you get finally this moment. So this is the final moment that is being obtained, and from this you can calculate the reactions. So similarly, you calculate the reactions by MAB plus MBA divided by H. Similarly here, MCD plus MDC by H. Once you are done with this, you get these two values. You can see that now the summation of H equal to 0 for the frame is satisfied by these two reactions. Now, how to calculate the deflection? You know that this is an aluminium bar, aluminium frame, which has E equal to 69 GPa and I equal to BDQ by 12, where B is 15 millimeter and D is 2 millimeter. Then you convert it to meter power 4. Once you are done with this, you have delta equal to K times 1 by 96 EI, which will give you the 0.00066 meter, which is nothing but 0.67 millimeter. And this was verified by the Galgotias University machine calculations. So this equipment will show you the digital value of the deflection at this location, and you can see that this is 0.2 meters and this is 0.3 meters, and this weight is nothing but it is said to be the 500 grams, which is equal to 4.905 Newton. Okay, so you can see deflection is 0.60, but we have got 0.67 here. This is obtained. Then you can see moment is 0.123 and here moment is 0.1028. Okay, so approximate values are obtained and the reaction is 1.51, whereas we have got the reaction 1.412. So the machine calculations and the manual calculations are here approximate, and there may be some error with the load cell or with the dial gauge. So it shows some approximate readings and values. It's because of the machine calculations may be approximate when compared with the manual calculations. However, if we repeat the experiment from 2 to 3 times, we may be able to calculate the exact values. Thanks a lot for watching. Thank you so much. If you have any doubts, you mention in the comment section. Thank you.